All right, good day, everyone. Whether it's morning, afternoon, or evening where you are around the world, I want to welcome you to a transport biofuel, first of two transport biofuel sessions today as part of the IEA Bioenergy Triennial Conference of 2021, which is we run in 3-year interim. So this is covering the 2019 to 2021 period, and we'll start a new triennium in January. My name is Jim McMillan. I'm a co-task leader of Task 39, which has a transport biofuels focus. And today, the first session is going to be focusing on emerging biofuels markets and the importance of LCA and certification. As we've seen, the growth of biofuels in the marketplace, there's been an increasing, rather than going to mandates, there's been an increasing focus on looking at climate change mitigation as the primary driver for using low carbon intensity or low greenhouse gas intensity biofuels. And so we've got a series of 5 speakers today. They're going to give us cover this field of transport biofuels, focusing on approaches that have promise for marine fuels, as well as looking at life cycle analysis, which is really the key to understanding the sustainability of biofuels pathways, and increasingly is the frame within which we're analyzing biofuels. So welcome again to this first session of IEA Bioenergy Task 39. The second session will be later today, and will be focused on aviation fuels, and my co-chair, my co-task lead, Jack Sadler, will be leading that. We'll be moderating that session. So just a few items, housekeeping items before we start the session. If you have questions, and we encourage you to have questions and to submit them, please use the Q&A button for that. We also will be running a poll, and when I finish my remarks here, we'll kick off that poll just to start to get engagement of the audience in the webinar. So without further ado, I would like to introduce or begin the transition to the first presentation, which will be my Task 39 colleague, Suni Thompson, discussing progress towards marine shipping, biofuels for marine shipping, and status and identification of barriers in the marine sector. And this is a huge opportunity for biofuels. So before Suni starts his talk, I'd like to run the doodle poll and the poll, and so hopefully Marco can get that running. So Marco, is the poll up there? Okay, yeah. So the poll, you'll see the poll in the down at the bottom of your screen in the chat area. So please fill that out. Thank you. And then and so now I'd like to turn it over to Suni for the first presentation. Suni, the floor is yours.
Thank you, Jim. And I hope I come across clearly now.
Yes, you do.
I am Suni Thompson from the University of Copenhagen in Denmark. I'm associate professor there, doing research in biofuels and biorefining. And I'm also the Danish task member in Task 39 of IEA Bioenergy. And as part of that, we have prepared a report looking into the progress towards biofuels for marine shipping. And especially we have been looking at the status, but also try to identify barriers for utilization of advanced biofuels in the marine sector. And of course, as Jim just mentioned, the main driver here could be said to be global efforts towards climate change, but there are also specifics associated with the marine sector, where I will just outline a few of those things in an initial justification of this work. And of course, we need to make these slides work. Yes. So first off, There are two major emission types from the marine sector. One being on the sulfur emissions, where traditionally there have been upwards of 4% of sulfur in the marine fuels. And in the past decade, or a bit more, these emissions have been decreased quite a bit to be below 1%, especially in emission control areas of the coast of Europe and the Americas, and potentially also in other areas in the future. The emission of sulfur needs to be significantly reduced, which poses a challenge for the existing fuel types. Furthermore, the International Maritime Organization has also imposed targets for reducing the carbon intensity. Already in 2030, we are aiming at reducing with 40%, and for 2050, it's a reduction of 70% of the carbon intensity seen in 2008 that we are aiming for as binding and also quite ambitious targets. So as the marine sector is a sector that cannot really change from day to day, the ships being built now should last for decades. So for that reason, the shipping industry will really need to turn around now. And we also see those changes starting to take place. The main challenge we see is, even though that renewable energy is increasing, the investments in biofuels over the past decades have been quite low, especially when looking at making real capacity. Then the investments have been lagging a lot behind other renewable sectors such as solar and wind, which is a shame, since especially for the marine sector, biofuels seem to be a perfect fit for many reasons. One of them being that the fuels and the feedstocks are extremely low in sulfur, so we are addressing that problem very direct. A second being that second-generation lignocellulosic feedstocks are very abundant, so we would be able to cover the need in the sector if we are producing the fuels. And then there's a third, more specific link between biofuels and the marine sector, which is that the marine engines in the ships are actually very adaptable, in the sense that they can take in fuels that are more problematic than other sectors can do. Imagine how they are now running on bitumen-like residual fuels. In the same way, the ships would also be able to run on other problematic and therefore also cheaper fuels, thereby not being in direct competition with, for instance, aviation or road transport. We have also seen quite a lot of different fuels being proposed from different biosources, all the way from biodiesel as we know it in road transport, to more emergent biofuels like syngas from gasification, or upgraded biocrudes from hydrothermal liquefaction, and also alcohol fuels, gaseous fuels, and so forth. So there's a lot of different fuel options, and many of these are actually fitted well with the marine sector. We are luckily also seeing a sector which are aware that they are middle of a change. Here we see a quote from a collaborator of mine working with Maersk, which are very much aware that we see big changes right now, even though we are not completely aware of where the change is leading us. So we do have all these obvious reasons of why biofuels and the marine sector is interconnected, or could be interconnected in the future to a much larger degree than we see now, with especially the focus of reducing both sulfur emissions and greenhouse gas emissions. Unfortunately, we have not seen in the past 5 years or 10 years this specific fuel that have penetrated the market. We have not talked to any stakeholders which have at this point dedicated themselves to any single fuel, and we haven't seen any single fuel really taking over large shares of the market. Different fuels have different qualities. Drop-in fuels, for instance, are easy to use now, as no adaptation of engines are needed. They're challenged on supply and on costs. We also see emerging fuels, where we have great potential, but where the infrastructure and compatibility issues could be challenging. To that, a note could be that we haven't talked to any stakeholders who are actually very worried about this part. They all seem to think that the technical issues are some of the issues which are easier to solve, especially over time. And one way, for instance, of solving that we have already seen is that more and more ship owners are installing new engines. So they're retrofitting their old engines or installing new engines in the ships. For instance, multi-fuel engines, which can cope with more than one fuel, which have been seen in several occasions. So in the recent report, which we started the work with that a bit more than a year ago, we have this initial knowledge that the sector would benefit from biofuels, and the other way around, that it was a good match. But we wondered why we didn't see that big market penetration yet, which we might have anticipated just 5 years ago. So we set out to identify those barriers which would be there, apparently have been there, to keep this large penetration of the market. So we looked into the background, we analyzed literature and other sources, and we also made a series of stakeholder interviews, talking to major stakeholders within the sector. This report is now available for everybody, so you can download it from the IEA homepage. And similarly, you can also download the previous report from 2017 at the same location. I will actually let the details stay in the report. And of course, we identified a whole range of barriers, which were all important to certain degrees. But I will jump to the conclusion, where we identified the three, in our opinion, and from the data available, the three most important barriers that we see in the market. And the first of these are uncertainty on sustainability criteria. And with that, of course, there's a need of sustainability criteria. If we have to discuss how we can decrease the greenhouse gas emissions, we need to know how to measure that. And what have been seen in the past decade is that these criteria change over time. And when you make investments as large as they are doing in the marine sector, just retrofitting one ship to a new fuel, you need to be quite sure that the fuel you are switching to is also considered sustainable in 5 years' time, 10 years' time. And therefore, we see a lot of uncertainty connected to the uncertainty in the regulatory framework defining sustainability. And there is really a need within the sector of having these long-term sustainability parameters in order to move forward. It's not only connected to legislation, it's also connected to public opinion, because a little bit of that extra cost, which is associated with using sustainable fuels, could be covered by customers willing to pay more for sustainable transport. And for that reason, public appearance and public opinion about sustainable fuels is also very important. Another major barrier that we identified as being one of the most important ones are incompatibility of marine fuel standards. Right now, all marine fuels live up to certain standards given by the current ISO standard of 8217, which is a standard developed for looking at fossil fuels of the kind that you would use in a ship. The problem being that most biofuels simply cannot live up to this standard. It could be that they are low flash point, that they have different viscosity, they might have a different ash content than a normal fossil fuel will have. That is not necessarily a problem when using the fuel in a ship. And many ship owners and engine developers do not see a problem with these new fuels. But if we want to take the next step and be able to bunker these fuels, not only in a specific port in Denmark, let's say, but also in Singapore, in Rotterdam, in Vancouver, all over the world, we need to agree on standards so you could bunker the same fuel all over the world. There are initiatives like interim guidelines from the IMO on the alcohol fuels, which really help along, but there's a need for really, again, international standards that we can live up to and where we know exactly what we get when we bunker. Again, it's important to state that the R&D efforts are going on despite the lack of standards, but if we really want to see market penetration, we need the standards there. The last and maybe also most important barrier is lack of economic incentives at this present time. Right now, the overall cost of using fossil energy is just lower than the overall cost on bio-based alternatives. There are many reasons for that. One being that the biofuel sector would need to build up a new industry. Another being that the subsidies for fossil fuels have been a lot higher than subsidies for biofuels. But the point of it is that it's just cheaper to use fossil energy than bio-based sources. And therefore there's a need for targeted policies and incentives. It could be in the form of renewable fuel mandates. It could also be subsidies, or it could be even carbon taxation. And for that reason, we are looking at the IMO, at the COP negotiations and other international collaborations, because it's again crucial that these things are targeted on an international level. And without our interviews being a real what you could call a quantitative study, we did talk to many different stakeholders, and what we hear is that they are advocating mostly for carbon pricing. And it seems that that would be the easiest measure to really have on an international basis. So now I have really outlined here some barriers, and I still want to end on a positive note, because I am completely sure that biofuels fits very well for the maritime sector. And we also see a lot of very ambitious companies who see a competitive edge in being first movers here. So they are already doing a lot of R&D and moving towards a lot of sustainable fuels in the sector. But it's also clear that we could accelerate this development significantly by lowering the investment risk related to biofuels in this sector. And we do that by having long-term international sustainability criteria, fuel standards, and international policies and economic incentives that really could act as a foundation for this transition. So with that, I actually just have left to say thank you for inviting me. Thank you to the organizers, to the task, to IEA Bioenergy, and also to the co-authors for doing a great job in this report. Back to you, Jim.
Thank you very much, Sune. Just setting up the parameters here, thank you for staying on time, and we have time for a couple of questions. The idea will be that we'll have a couple of brief questions after each presentation before we have a panel discussion at the end. So we have a couple of questions that have come in that I would pose to you. One is, the first one is from Lucas D'Souza, and it's what are the main challenges for the use of bioethanol as a marine fuel?
There are, of course, many challenges. One of them could be that public opinion about first generation, second generation is not always as positive. We see, of course, great sustainability assessments in cane-based ethanol and in second generation ethanol, but there are still discussions, and that can kind of keep some stakeholders from going there. Another could be that the energy content is on the low side, but there are efforts to raise that by doing blended fuels, by doing multi-fuels based on ethanol and so forth. So even though there are some drawbacks, I will also really see some great opportunities also with the alcohol-based fuels, and with some of the dual fuel engines that we see, the alcohol fuels are kind of the second fuel, you could say, that could be burned in those engines. So so drawbacks, but definitely also opportunities with alcohol-based fuels.
Thank you. So we've got a few more questions have come in. One was if you see a future for FAME, the fatty acid methyl ester type of biodiesel, sort of the old conventional biodiesel, not the renewable diesel that is seemingly more fungible and being used more widely.
Well, there is definitely problems on the supply side. I don't see us globally producing much more FAME, not sustainable anyway. So I would tend to look towards other fuels, and we should remember that this sector is really a big sector, and it's a lot of fuel that we would need, a lot of extra additional sustainable fuel. So I definitely see FAME on a short-term basis to be kind of an initial fuel, maybe a fuel that is used in harbors and in emission control areas. But on the long term, I don't see it as a major biofuel in the sector. That's my opinion.
And would you, but is that because of the limitations in the oleogenous feedstock? So it would also apply to renewable diesel, not just to biodiesel or to the FAME biodiesel? That comment?
Yeah, especially, but I don't want to be too rough here, but unless we see new production organisms really taking speed, like microalgae or something like that, I have a hard time seeing that we would really take out a major part of our agricultural lands or new lands for producing lipids. But again, that's on me. We'll see.
Right. We need sustainable palm to become a reality and not just an aspiration, since palm is about twice as productive as any other terrestrial crop we have for getting vegetable oil. So yeah, well, thank you very much, Sune. I think in the interest of keeping the session on time, I'll hold the questions for there, but we will have a panel discussion at the end. So everyone, please keep those questions coming, and we'll go through more of them during the panel discussion. So with that, I'd like to switch gears and introduce our second speaker, Thijs Lammens from BTG Liquids. He's in the Netherlands. He's a senior process engineer there. So we're staying in Europe, staying with the European focus. And I won't belabor your introduction further, Thijs. Welcome to the session, and the floor is yours.
All right.
You need to share your presentation, I think.
Yes, I will do so. Thank you very much for the kind introduction, Jim. Let me share my screen with you. There we go. And now. Okay, so you should be seeing my presentation now.
Yes.
Good. So thank you again for the kind introduction, Jim, and for the invitation to present here. I'm honored to be part of your conference. What I want to talk to you about today is about a specific technology pathway to produce advanced biofuels, namely from fast pyrolysis bio-oil. I have split my presentation into two main parts. One of them about BTG Bioliquids, the company I work for, and fast pyrolysis in general. And the second and major part of this presentation will be about the refinery processing of fast pyrolysis bio-oil. And then I will end with a summary and conclusions. First, about BTG Bioliquids. We are a technology provider. So we are a company that provides fast pyrolysis technology to convert biomass residues into a liquid called fast pyrolysis bio-oil. We consider ourselves product leader with 3 commercially operational plants, and we are committed to further roll out the commercial deployment of this technology. Fast pyrolysis bio-oil is explicitly made from lignocellulosic biomass residues, so second generation or advanced or whatever you want to call it. It doesn't compete with the food chain. A few more words about the current technology deployment that has been going on. Here you see pictures of the 3 operational commercial fast pyrolysis plants with our technology. The first one was started up in 2015 in the Netherlands, close to our main office in Hengelo. It's called the Empyro plant. We sold it about 3 years ago to Twence, a waste processing company, because of course we are a technology provider. We don't aspire to run our own production facilities. And then there's the plant in for Green Fuel Nordic in Lieksa, Finland, that started up about a year ago. And more recently, pyrocell in Gävle in Sweden started up last summer of this year. About fast pyrolysis, very short. I think most people are familiar with the technology, but it's a thermochemical decomposition of biomass. So you heat up lignocellulosic biomass really quickly in a few seconds to about 450 to 600 degrees in the absence of oxygen, so that you do not combust it, but you crack the molecules and turn the biomass into a liquid. And this liquid is called fast pyrolysis bio-oil. Byproducts of the process are heat, and you can turn that heat, of course, also into power if you want to. Here you see an overview of the process as it's implemented in the Empyro plant in the Netherlands, but also the other plants that we constructed are very, very similar. It all starts with the biomass here on the left side that goes into a dryer, from where it goes to the top of the building to a buffer vessel. From the buffer vessel, the biomass goes into a reactor where it's mixed with hot sand, very quickly mechanically mixed, and then the biomass cracks into vapors. Vapors are separated from the sand and the coke that is produced just by gravity. They go up through a separator and cyclones to further clean the vapors to a condenser where the bio-oil is formed, which finally goes to a storage vessel. If you follow the solids in the process here, the sand and the coke that is formed, it goes down and then it goes through a riser with air into a combustor. Because of the air that's present and still the hot temperatures, all the char is combusted, and that delivers the heat, the energy that is required to keep this process running. It's completely self-sufficient. There's an excess of heat that's being produced in a steam boiler that is turned into steam, and the steam can further be used either to create the power that can be supplied to the grid and to operate the plant. And besides that, also what you can do with the steam is dry your biomass, dry the sawdust, for example, before it goes into the process, and even export it to an external customer. Overall mass and energy balance, a very general overview. These plants, they run on about 5 dry tons of biomass that goes in per hour. About 2/3 of that is turned into pyrolysis oil, and on an energy basis, about 1/3 of it is turned into heat and power. The difference between the two, so the loss of about 10% in this process, that is the heat that is actually used in the process to dry the biomass, for example, and to reheat the sand. Then about one specific project, the most recent project, pyrocell, the pyrolysis plant that is now running at capacity. It started up in September of this year. Pyrocell is a joint venture of Cetra, as a wood processing company, and Preem, a Swedish oil refiner. It produces pyrolysis oil from sawdust. As I mentioned, started up this year. It was delivered turnkey EPC by Technip Energies. They did all the construction. Pyrolysis oil production of this plant is 24,000 tons per year. And all this pyrolysis oil will go to the refinery of Preem in Leeskiel, where it will be co-processed to produce advanced biofuels. Delivering a greenhouse gas reduction of about 80 to 90%. And of course, these fuels are in compliance with EU legislation and also with the Swedish relevant legislation for advanced biofuels. Then I want to switch, use this as a bridge to go further about producing advanced biofuels from fast pyrolysis bio-oil through refinery processing. Let me start with the supply chain. The way we look at the supply chain from biomass to advanced biofuels is that you should convert the biomass into a liquid as decentralized as possible, so close to where the biomass is, so that you do not have to transport the biomass itself. In the example that I just showed from pyrocell, for example, it means that the pyrolysis plant is co-located on the same site as the sawmill, so that the sawdust that is liberated in the sawmill doesn't need to be transported. It just goes onto a belt directly into the fast pyrolysis plant. So it really saves a lot on transport costs and also environmental impact. Additional benefit of not shipping the biomass around the world is that you can return the minerals to the soil where they came from. Then if you have produced the pyrolysis oil, you can transport it much more easily. It's liquid, it's 10 times denser than solid biomass, so it just makes life more easy if you want to transport it. And then finally, you can process it in a centralized location, such as, for example, an oil refinery, making use of existing infrastructure. Then there are different ways in which you can do it. You can create transport fuels from fast pyrolysis bio-oil. This is a sort of a general scheme to illustrate it. What you see on the top is a very simplified supply chain from crude oil through an oil refinery to transportation fuels. And then what you can do is bring in the biomass in a liquid form through at various points into this supply chain. So what you can do is the fast pyrolysis bio-oil, the crude bio-oil as we produce it, can be fed, co-fed in a fluid catalytic cracker, for example, in an oil refinery. So you can feed it directly, but what you can also do is first do an upgrading step, for example, a hydrotreatment step to stabilize the oil, to deoxygenate it partly. And in this way, you can either co-process larger volumes, for example, in your refinery. You can use different units also, potentially hydrotreaters, for example, instead of just fluid catalytic crackers. What you can also do is completely deoxygenate the pyrolysis oil to a product that's referred to as mixed transportation fuel, which is essentially a barrel of completely bio-based crude oil that you just need to distill to make fungible fuels. What I want to talk about further today is this pathway, just the direct co-processing of fast pyrolysis bio-oil because it has some specific advantages. It's very low in capex. It's a short time to market. It's a commercial technology already. And with that, it can deliver fast greenhouse gas reductions. Then about fluid catalytic cracker. I mentioned the unit already. It's what we see as the pyrolysis oil gateway into a refinery. And that's because this unit specifically can deal with water, it can deal with oxygenase and with the coking tendency of fast pyrolysis bio-oil. The FCC has many possible outlets for its products, as you can see in this very complicated refinery scheme on the right. All the red arrows are all the different routes that FCC products can go. So almost any product of a refinery can consist for a part of FCC products. Of course, that brings a challenge when it comes to, for example, certification and legislation is how to track the green content if it goes to all these different products. Before I go into that question, a bit more on how this process works. That's what you see in the scheme on the left side. It's a very simplified scheme of an FCC unit. It's a system with a riser reactor and a regenerator. So there's a circulating catalyst that goes around. You feed a regular fossil feedstock at the bottom. It comes into contact with the hot catalyst, and then the feed is cracked into various products. What you do when you co-process fast pyrolysis oil is that you co-inject it, and you use separate injection system to inject the pyrolysis oil into your unit. And then as soon as it gets into touch with the catalyst, your biomolecules are cracked and everything is mixed together. And that means that your biomolecules are cracked together with your regular feed, and they end up in all the different products that you make in your FCC unit. Commercial operability of these units is proven. There have been several refinery trials with FCCs around the world of typically 1 week operation, co-processing with fast pyrolysis oil, and that showed that there's no operational issues. Also at pilot scale, it has been shown that you can go up to around 10% of co-processing of fast pyrolysis oil. Then what happens to the yields is of course a question. If you co-process around 5% of pyrolysis oil in an FCC unit, it has very little impact on the overall FCC product yields. Obviously, the 95% is regular feedstock, so you don't expect too much effect on the overall yields. But you can see some effects. What I show here is some data that is already quite old by Petrobras. It was published. They showed that typically your gasoline yield increases if you add pyrolysis oil. LPG yield stays about the same, and some other yields they decrease slightly. The oxygen that is present in pyrolysis oil that is turned into CO, CO2, and water. And then what you see on the right side in the graph is the yields if you sort of subtract the fossil part and you only zoom into the bio part of your FCC yields, then you see a very high gasoline yield. That's probably due to the relatively low molecular weight components, sugar type components that are present in your bio oil. They turn into gasoline. And then you see an LPG and an LCO or FCC diesel yield. And some components they show negative yields. And that's probably because of synergistic effects that decrease these yields from your FCC. Also, you see here the CO, CO2, and water, which are fully attributed to the bio-based feedstock, of course, because normally you hardly produce any of these products if you run only fossil feed to an FCC unit. Then about tracing biogenic content, I already mentioned earlier in my presentation that this can be quite a challenge when it comes to FCC products, and then if you co-process fast pyrolysis bio-oil. In general, when you talk about certification of biogenic products, these systems, when it comes to co-processing, they are based on either radiocarbon determination or C14, or they are based on bookkeeping methods such as mass or energy balance methods. When it comes to products with a high biogenic content, so for example, 100% bio-based chemicals or like 100% HVO product, the tracing of it is relatively easy. But in this case, there's quite a unique set of challenges. If you co-process fast pyrolysis bio-oil, the scale difference between a pyrolysis plant and a fluid catalytic cracker is roughly 1 to 100. So the complete output from one pyrolysis plant, as the tree that we built currently, is equivalent to about 1% of the input of a average European FCC unit. In the US, they are even a little bit larger. The co-processing volume is limited to about 5 to 10 weight% to avoid operational issues. And that means that the biogenic content, because it's distributed across many refinery products as well, it's very dilute. And we've shown that radiocarbon analysis is really unfeasible. It's not accurate enough for these kinds of products, and that makes bookkeeping methods a necessity. For more details, we published a paper on this on our website. But that's when it in relation to certification of this method. Then, because this session of the conference specifically mentioned LCA as being important, so I didn't want to leave out any LCA work that we've done. So here you see an LCA case study to end my presentation with co-processing fast pyrolysis bio-oil. In this case study, what we did is we looked at the Finnish fast pyrolysis plant as an example. It uses sawdust. We did economic allocation of the impact of the wood processing and the whole supply chain beforehand, of the emission impact to the sawdust. So it's a bit more stringent than what the current Renewable Energy Directive legislation says, which is that you can just start with 0 emissions if you use a waste product like sawdust. But yeah, we allocated it economically, and then produced the fast pyrolysis oil to be shipped to a fictional refinery somewhere in Western Europe. So you can think of the Netherlands, Belgium, France, the UK, somewhere in that direction, and then 5% co-processing in an FCC using the data, the public data as published by Petrobras. So in this analysis, what we found is that the production of fast pyrolysis oil, the impact of it is limited to about 1.7 grams of CO2 equivalent per megajoule. So it's fairly low. In the graph, you can see it as sort of this bottom bar. About 40% of that is due to the grid electricity that's needed for running the process, and about 40% is just some LPG that we use for starting and stopping. So as I mentioned, the process runs by itself. It's self-sustaining, but just to start up, to heat the plant before we start production, you need some LPG, and that has an impact, of course. Then what we found is that the majority of the impact in this case, of course, if you transport the pyrolysis oil from Finland to Western Europe, although it's much more sustainable than if you would transport the sawdust itself, still there's a significant impact. 60% of that impact was the trucking from the northeast of Finland to the harbor. And then the other 40% of the impact is the ship transport from the Finnish harbor to a refinery at a harbor site in Western Europe. So that's about 3,000 kilometers or so. So that's also quite a significant impact. Those are the other two bars that you see here. So that's the majority of the impact of this case study is really the transport of the pyrolysis oil. But despite it, still we saw an overall impact that's relatively modest. So we saw greenhouse gas emission reduction for gasoline production through this example of almost 90%, which is quite good, I would say. And yeah, if you would use the pyrolysis oil, convert it closer even to where it's produced, this could still dramatically reduce further the emission reduction. In summary, I hope that I was able to show with this presentation, first of all, that fast pyrolysis bio-oil production has reached commercial maturity. There's currently 3 operational plants with our technology. Furthermore, advanced biofuels from pyrolysis oil co-processing has a high potential. It's low in capex, it's short time to market, and with that you can achieve fast greenhouse gas emission reductions. So you can start tomorrow if you want. And then I've hopefully shown that feasibility of it. The co-processing in an FCC unit is proven up to 5 weight %. Operability has already been demonstrated at commercial scale, so in actual refineries. FCC products show a favorable gasoline yield, so that's a bonus. And of course, the exact yields, they will depend on the specific unit, the feedstock it uses, and the process conditions. Tracing biogenic carbon in this process is a challenge. It will require a bookkeeping method. And I hope that I showed you with the LCA case study example that there's a very high potential for greenhouse gas reduction through this pathway. That's it. Thank you very much for the attention. And if there's any questions, I'm happy to take them. And otherwise, I'd like to give the floor back to Jim.
Thank you very much, Thijs. And we've got a few more questions, and I encourage people to use the Q&A button to keep submitting questions. One from Lavanya Misala, and I apologize if I'm not getting your name correct. Is there any post-treatment conducted for pyrolysis oil for improving stability, and what is the process followed for removal of miscible water from pyrolysis oil?
That depends. So in the major pathway that I showed, the co-processing in an FCC unit, there is no post-treatment. So the crude oil can be used directly, which means it contains about 25% water. I always like to say, refer to pyrolysis oil just as a liquid tree, so liquid biomass. It has all the oxygen that is in the biomass. It's still in there. So if you would remove all the water, then your pyrolysis oil becomes solid again. So you cannot remove all the water. So you can remove part if you want, but if you go if you would go below, say, 10% or so, then you're just a solid. So the viscosity is directly aligned with the water content. So you can remove part just by vacuum distillation, for example. But if you use an FCC unit, it's not necessary. You can just feed it directly if you want.
Thank you. I guess another question, there's a number of them, and I would encourage all of the presenters to look in the Q&A panel and answer some of the questions that are up your respective sort of presentation alleys, because there's some on marine, there's some on pyrolysis and so forth already there. Another one, and I think this is really key, it's a very promising approach for leveraging our petroleum infrastructure if we can co-process in petroleum refineries. I think this is a wonderful developments. What is limiting, this is from Andrew Corbin, what is limiting the application of fast pyrolysis bio-oil in the FCC to 10%? Can this content be further increased? And I think that's a key to getting, so we can be using a higher and higher share. Mm-hmm. Any thoughts on that?
Yeah. I would say the coking tendency of fast pyrolysis bio-oil, it's relatively high. That's because there's still quite some sugars in there that are relatively reactive. So if you go too high, then your heat balance doesn't work out anymore. You produce too much heat in your FCC unit. That's currently limiting the co-processing percentage. What you can do about it is I've showed the other pathways where you do a mild hydrotreatment step, specifically targeted at reducing these kind of reactive sugars, turning them into alcohols. And in that way, you can really start going up to higher numbers, say 20, 30, maybe even 40% co-processing. Because then, yeah, that's not the limitation anymore. So I would say that's the major step, the major gain that you can do with pyrolysis oil to go to higher. It takes a bit more development still. So it's sort of a stepwise pathway that you can increase volumes in this way, but it is certainly a possibility.
Thank you very much. That's very encouraging to hear, and I look forward to future developments in that area, getting the co-processing percentages higher. So I want to thank you again, Thijs, and we'll bring you back at the panel. I'm going to now turn the floor or introduce the next speaker. We're going to turn to, we've been in Europe, sort of focused in Europe, but we're now going to turn to South America and sort of a look at the rest of the world and emerging economies that have good potentials for biofuels. And Glaucia Mendes Souza, professor at the University of Sao Paulo, and incoming deputy task leader for Task 39. We're honored to have her presenting on this topic. It's one of Task 39's projects that Brazil, under Glaucia's leadership, has been leading up. So Glaucia, the floor is yours.
Thank you. Hello, everyone. Let me just share here my screen.
And we are seeing it, so thank you very much.
Okay. All right, so I'm Glaucia Souza. I'm the coordinator of the FAPESP Bioenergy Research Program, BioN, and national team leader of Task 39 and Task 45. I'll be talking about biofuels production and use in emerging economies. Let me just minimize here. Okay, the gallery. All right, so this is the Brazilian team that is evaluating biofuels in emerging economies. This work we started 1 year ago, approximately, and we intend to carry it over towards the next triennium. Okay. Our motivation was, it started when we conducted bioenergy sustainability analysis of Latin America and Africa. This was done in collaboration with 100 institutions from 31 countries. Under the Aegis of Scope, we produced a policy brief. And one of the conclusions of this policy brief, considering that these regions have many insecurities, was that R&D targeted at bioenergy could benefit also food production and land preservation, and that there was a large potential of biofuels production in these regions. We have around 500 to 900 million hectares of land available that could be used and would not compromise food security or biodiversity. And remember that we have 30 billion hectares of pastures in the world, and only 40%, 60% of this pasture has any livestock on it. 40% does not have any livestock, so we could improve efficiency of pasture use in these regions. So we started a work that intends to integrate TEA, life cycle analysis, and exergy analysis to define key performance indicators that could show us where it could be, we could improve sustainability in the process. We looked, at this point, we have looked at feedstocks and conversion data. We have agricultural indicators analyzed and done an initial life cycle assessment in 4 countries. So we started with Argentina, Brazil, Colombia, and Guatemala. These are their national biofuels program as it stands. Argentina has a new policy since July this year. They are currently adopting E12 and B5. It's fully implemented, and Argentina exports biodiesel to US, Europe, and Latin America. Brazil has started in 2020 the Renewable Bio program. This year, it aims to save 24 million tons of CO2 emissions. We currently have, this is interesting, pure ethanol in all gas stations in Brazil. We don't have pure gasoline. We have E27, so 27% of ethanol mixed to all gasoline, and also B10, and a large flex fuel engine fleet. Colombia has started their law in 2001. It was implemented in 2002. They are currently using E10 and B12. Guatemala has not adopted the national biofuel program yet, but it's planning. Looking at the agricultural indicators for corn, sugarcane and soybean in Argentina, sugarcane and soybean in Brazil, sugarcane and palm oil in Colombia, and sugarcane in Guatemala. There are lots of things that we can get out of these numbers, but I want to point out this agricultural energy ratio that I'm highlighting for the sugarcane case in Argentina, Brazil, and Colombia. And look at how bigger this gets, how better it gets when you have high yields of the crop. So this indicator is the ratio between biomass energy and crop production energy consumption. So I will come back to this point, but I want to highlight the need for high yields. We calculated emissions for sugarcane ethanol in Argentina, Brazil, Colombia, and Guatemala, and also for corn ethanol in Argentina. You can see them, most of the reductions of the emissions come from the farming side, except in Argentina, the ethanol production could be improved. They are using natural gas in the process. We also evaluated emissions with biodiesel. The main point is that there's always large reductions of emissions by using these fuels. And we calculated the energy indicators, net energy balance and energy ratio, them all being more than 0 and 1 here. This means they are all energetically sustainable. And then we look at what impact could we expect if we had a policy that would reward low carbon fuels. So we use the example of Renewable Bio. Renewable Bio is a market-driven incentive for pricing externalities. It is transforming social and environmental costs of using fossil fuels into revenues for those that can be certified to reduce emissions. It uses a life cycle analysis. It disqualifies biofuels that are produced associated to deforestation. All this is done without additional taxes or subsidies, without setting volumetric targets, and without establishing a captive market. This is the policy framework of Renewable Bio. We have here the agents, the actions, documents, and tools. The way it works is that our National Energy Agency defines individual goals for distributors that have to acquire C-bios that are decarbonization credits sold in the stock market. The credits are issued to biofuels producers and importers that can be certified by a third party that they are reducing emissions. And we have a Renova calculator that all the data is transparent, it's public on how this life cycle assessment was done. We try to imagine with the current production, we calculated with the current production of biofuels in these 4 countries, that we were already having around 45 million tons of CO2 avoided using ethanol. And if we had a CBio cost of $10, we could calculate around $450 million that would be made by the producers, that would return to the producers as revenue that could be used for innovation. And the same was done for biodiesel. So in total, we would replace with the current replacement that is taking place of 60, decreasing 65 million tons, 30 million tons of CO2 equivalent. We would be having around $630 million of revenues for these activities in these countries. And then we looked also at land availability, considering the relative amount that we have land used for biofuels in this country. So the squares here show the amount of land in respective to the country total land area, and how much of this is being used for cropland and pasture, and how much would we need to double the production of biofuels in these 4 countries. So this is the amount of additional land that could be from pasture land. Look at how little this is in comparison to the amount of pasture lands that these countries have. We did this for ethanol and for biodiesel. In summary, we would need 4.5% of pasture land conversion to crops in Argentina, around 6 in Brazil, 0.2 in Colombia, and around 10% in Guatemala. This was the largest percentage to duplicate, to double the productions of biofuels. We did previously a similar study that was published last year, where we did we made calculations for 20 countries in Latin America and Africa, considering the current yields that we have in Brazil. Now, I think the present study that I just showed is an improvement because we are considering the local conditions. But in this study, we also calculated with 1% of pasture used for biofuels, we could get to around 50 million tons of avoided emissions. And for Task 45, we did a study, a review on the payback time, how long it takes, and the best practices for land use. So there's a lot of lessons learned already for these biofuels. There is lots of new technologies in use. But what we see is that if you convert cropland to sugarcane, the payback time is 0. If you convert pastures into sugarcane, there is an initial debt, and then you have you need around 2 to 3 years to start the soil, to go back to initial levels of carbon in the soil. And you don't want to do this, which is the scenario where you convert cerrados to sugarcane. Then you have 8 years of payback time. It's not worth it. But this partial conversion to sugarcane is a very good route. So in conclusion, we see that the biofuels produced in these countries is energetically sustainable and that they lead to significant reductions of emissions as is. And that to expand, we would need around 5% of their pasture lands to be able to duplicate. That this could bring revenues, and we could innovate in these regions. We need innovation or significant improvement in farming activities and stop using natural gas, go totally renewable. So lots of opportunities for R&D here. And I want to focus on these last 2 points in regards to yields. I mentioned how the large impact that the higher yields in Colombia have on the agricultural ratio. So we have some good news here, research efforts that are rapidly stepping up. We have sequenced the sugarcane genome. We have a lot of biotechnological answers to some of these challenges, including the production of bioproducts. All that I talked today was about sugarcane in these countries, but we have the energy cane in trials already in many mills that if they could be integrated to these processes, we could have a lot of bioelectricity done, excess biogas, decrease feedstock competition, and also increase the amount, the possibilities of 2G being integrated. We developed higher biomass genotypes. This is recent work from my lab in Brazil, and future climate resilience. This on the right is sugarcane, total biomass, tons per hectare, commercial sugarcane in pink. The green is the energy cane that I showed, and we managed to improve even further tons per mass of biomass per hectare in these new clones that still keep some sugar on it. So this is really good news. We are very happy to see this progress. And the next step, we need to look at the economic indicators of the current and the futurely what we expect to have coming. We also want to analyze exegetic indicators. I like this renewability index here that will show eventually with the use of all these residues, we could improve, expect great gains here. And we want to expand to these other countries as well. So we are at this point here of integrating the 3 different analyses. So I want to finish by thanking my colleagues that participated in this project, especially Nicolas Canabarro and Pablo Ortiz, who are doing the heavy lifting of the project. Thank you.
Thank you very much, Glaucia. There's a few questions here. One, I wanted to go back to your original slide where you showed those big differences in the, what was it, the agricultural energy ratio, or I'm not sure exactly how you defined it, but why was it seemed like the productivity of cane in Colombia was much higher than the productivity of cane in Brazil. And so could you comment on that?
Yes, they have the perfect environmental conditions. So it's naturally very good for sugarcane. They also do this in valleys with the good precipitation conditions, but the land is not, they don't produce as much. So they don't have a lot of land in these conditions to produce it. So it shows how high we can go by managing this more adequately.
Thank you. Yeah, so great potential. And I think it sort of speaks to your going along with the genetics to improve the strains. You know, those two go together very nicely. Helen Biwi Comesa, and I apologize if I'm mispronouncing names, which I'm sure I am, asked if you've looked at land use change, direct and indirect, and the potential repercussions in terms of GHG reductions.
Yeah, so this was done a while ago. We looked a couple of years ago at if there was an impact of, for instance, sugarcane going into pastures, and then food production invading Amazonian lands and things like that? And the answer is no. There's very little evidence of what's happening. If you look at land occupation in Brazil, it has mostly increased. Bioenergy has expanded mostly into pastures. So this scenario that I mentioned is already happening, of expanding into into pasture. So we expect that with multi-cropping and also double cropping, as is already happening, and bringing in corn as well, we don't expect large changes, and we have the pasture land that could be used.
Thank you very much. So I think we'll leave it at just in the interest of time, and bless you. But in the interest of time, we'll say thank you very much and bring you back at the panel time. And I will now introduce our next talk. Again, we'll be going back to Europe after looking at South America, but it is a global effort here. And we've got Jose Muzerts from the Netherlands Enterprise Agency, RVO, who's a sustainable energy advisor there, going to be speaking on the very important topic of certification in the development of biofuels. We've talked about the sustainability, and certification is all about how you prove it or get the official parties to accept that you have a good product. So Jose, I turn the floor over to you. Thank you very much.
Thank you, Jim. I hope my screen is already shared, or?
No, it's not shared yet.
Okay.
I'm just seeing you. But
okay. I'm not sure what's happening now. Let's have a look.
And I again encourage all the presenters to look at the Q&A, look through the Q&A. It's getting quite extensive, and to answer questions that are appropriate to you. Yes, we can see your presentation now. Jose, thank you very much.
Thank you, Jim, again. As Jim already mentioned, Jose Muzerts. I'm working at the Netherlands Enterprise Agency on renewable energy in transport as a policy advisor. And this presentation is on ongoing work to identify certification scheme improvements related to sustainability and greenhouse gas emission aspects of biofuels. It's the Task 39 project. It's a collaboration between the Netherlands Enterprise Agency and Jinke van Dam Consultancy. Phase 1 that's ongoing now is on reviewing biofuel policy frameworks, and phase 2, scheduled for the next triennium, will be on certification schemes. Okay, I'll try to. Yes, I hope this is all right. Why this study? Well, as already mentioned in this session before, emission reduction and climate mitigation are the driving force behind the production and use of biofuels. And because of that, the importance of overall sustainability and reduced carbon intensity has become more and more a priority. However, market implications of policy requirements related to these sustainability and greenhouse gas emissions are often difficult to oversee. And besides that, concerns on certification integrity might limit biofuel sales. So what we want to address with this study is to provide a better understanding of the coherence between policy requirements and sustainability certification. And in this way, we intend to support decision-making of parties involved in biofuel supply chains. The overall focus of this project is on non-conventional advanced biofuel supply chains. And it appears already that the definition of advanced is an interesting item to analyze for trade policies, because it can refer both to the bio feedstock used as well as to low carbon intensity of the fuels. As mentioned, phase 1 is on reviewing policy frameworks and to get a better understanding on the level of alignment of differences between policies. The analysis will focus on issues like sustainability requirements, monitoring compliance, CSC, chain of custody management, and traceability and transfer of data within the supply chains. And I will go into these topics in more detail in a moment. Several national policy frameworks of the task 39 members are included in the analysis, and with respect to the US, the focus will be on California low carbon fuel standards. And for Europe, besides the overarching EU policy on biofuels, the Renewable Energy Directive, some of the national implementations of this policy in some member states has been also taken into account. In addition to input from Task 39 members, we are glad that we received also information on the ICAO CORSIA policy framework on aviation biofuels. And the ICAO CORSIA policy currently covers over 100 states. The proof of compliance, I want to start with that. Proof of compliance to meet sustainability requirements. Several ways can be used here, several options are available. Can be obtained by using verification, so without certification, and solely by assessment and validation based on data. Furthermore, by certification, by independent private systems, and also by a combination of these two both mentioned. What we observed so far, and that was that in case of verification, data quality is key. So something about the quality of the data has to be also in the policy requirements if only verification is used. When using certification schemes, a clear policy framework with detailed minimum requirements is required for alignment reasons, because the certification schemes have to come up with the same results at the end. And furthermore, certification systems appear to be flexible to some extent and adapt to specific policy frameworks by the development of modules. An example for this, for aviation, ICC certification of sustainable aviation fuels has several certificates, each with its own requirements, set of sustainability requirements, set of verification requirements, acceptance of certification schemes. And it's all about aviation biofuels, but using different modules of the ICC scheme. With respect to the chain of custody of a biofuel supply chain, that refers to the way in which evidence is handled through the chain. Observations here are that most analyzed certification schemes make use of one or more different types of chain of custodies models, and the use of the mass balance model is the most common chain of custody model prescribed in the analyzed policy frameworks. In this mass balance COC model, the overall physical presence of the biofuels is relatively low when ranking different COC systems. And in this picture, you see the physical presence is decreasing from left to right. So this places higher demands on the paper trail and checks that accompany the fuel because of the less physical presence of the biofuel in it. So in other words, if it sets higher demands on the management of the chain of custody to ensure that biofuels actually find a way to the market. However, observations here were that despite those higher demands, the extent to which mass balance requirements are actually integrated in the analyzed policy frameworks, it's not the same. This is the case, for instance, for allocation rules. So the allocation rules are different, referred to in requirements of the allocation rules are different in policy frameworks. And this unclear COC management could lead to risks, as shown in this study here. For example, incorrect mass balance and allocation. The severity of these risks depends on the biofuel supply chain. Another topic that is analyzed is traceability and transfer of information in the chain. And as information about greenhouse gas emissions and sustainability requirements is transferred through the supply chain, that traceability offers the possibility to trace back the movement of a product or a fuel through the different stages in the chain. And that are the gray arrows in this picture. And observations here that we made was that the complexity with respect to traceability grows when the number of interactions increase, for example, between buyers and sellers, or the number of processed outputs increased. And this is also the case when multiple certification schemes are used in the supply chain, that are the blue arrows, and cross acceptance takes place. So one scheme is accepting the results of another scheme through the supply chain. Also, with respect to traceability and transfer of information, the first link in the supply chain or the point of origin is important. And requirements about the first link that is subject to verification of certification are often related to the feedstock that is used to produce the fuel. And information on the origin of the feedstock is key for its classification, either if it's a waste, the residue of a co-product. However, we have observed different non-harmonized interpretations regarding feedstocks. And as a consequence, the first link in the supply chain may differ depending on how the feedstock is categorized. For example, if a feedstock is categorized as a waste, only downstream greenhouse gas emissions have to be accounted from the point the waste occurs. And whereas in the case the same feedstock is categorized as a co-product, all the upstream and downstream greenhouse gas emissions have to be included. Information requirement at the end of the supply chain refers to both data to be submitted as well as to authorization of the competent regulating authority at the end that is checking the data. Information finally to be submitted to the competent authority for checking compliance differs due to different policy requirements. And we noticed that greenhouse gas requirements are generally covered, but there's more diversification for other, let's say, land-based criteria, example given for biodiversity, whereas in case of social criteria, there appears to be a main gap. The role of certification schemes on a global scale is limited, Their role is mainly in those regions and countries where they are recognized. And also it was observed that outsourcing public responsibility for monitoring to private certification schemes might be at the expense of public supervision. As an authorization for monitoring might be limited to the last link in the chain, whereas the sustainability declaration or certificate is overcoming the rest of the chain. So then the competent regulating authority can not go back into the chain to check data. And the certification scheme is covering the rest of the chain. Finally, a small quick glimpse into phase 2 of the project for the next triennium. The focus of phase 2 will be on risk and potential risk mitigation in the selected supply chains. And risks in this context refers to effectiveness and reliability of compliance. As already mentioned, risks can arise in different parts of the supply chain, at the point of origin of collection point, during trade and transport, and during production and blending, and even more locations. With respect to potential risk mitigation, in phase 2, policy-based certification schemes will be analyzed to identify scheme improvement opportunities. And besides insight in certification scheme improvement options, the additional goal of this project is to come to a better understanding of the coherence of legal requirements and certifications and its impact on biofuel feedstock supply chains, so trade flows. Because of a better understanding of this overall, it might support the decision-making of the different parties involved in the biofuel market. This is my last slide. Thank you for your attention. Back to you, Jim. I'm glad to take any questions.
Yeah, thank you very much. I'm not seeing a lot of questions in the chat, so I will just, in the interest of time, ask one, which is, what do you see as the, or do you see any developments on the international harmonization, the global harmonization? Because that seems like a very, especially for sectors that biofuels are now being targeted for, aviation, marine, which are very very international in character. It seems like a coordinated certification approach is needed, yet it seems to be very geographically specific at the moment.
It's really, the first results are that it's really regional, because although it's a global market, the certification is always adapting towards the policy framework where it is recognized. And therefore, we are very glad that we have the results of also the information on the COSIA framework, because that is covering the global market. So we are also comparing it with the specific requirements for aviation in Europe and on other markets. So I hopefully we can come up with some advice on that, and maybe we can predict something what's going to happen on those international in those international sectors.
Yeah, I think trying to recommend how to harmonize in the simplest possible way, but to achieve that, it's a really,
it will be a hell of a job.
Yeah. All right, well, thank you very much again, and we'll bring you back for the panel. I'm going to turn to our last transition to our last talk for today, for this morning session, or for this session now, with the focus on life cycle analysis. Our presenter is Don O'Connor. He's the president of S&T Squared Consultants, a consultancy focused on LCA, among other issues in Canada. And Don is going to talk further about life cycle analysis and its critical importance. Don, the floor is yours.
Thanks, Jim. And you can see the screen.
Yes, thank you.
So I want to sort of briefly cover four major topics here. One is the regulatory trends, which has already been talked about a little bit about LCA in terms of strengths and weaknesses, data, and areas that need focus for LCA development. So regulatory trends, bioenergy programs are transitioning in various parts of the world at different speeds, but we basically started with volume mandates, and then we saw some programs that had volume mandates but with GHG thresholds, so qualifying fuels had to meet a certain GHG requirement, and now we're moving to GHG emission reduction mandates, where it doesn't matter how much you use. What is critical is how much you are reducing the emissions, and of course the importance of LCA really wasn't that big a deal for volume mandates other than supporting policy. It became more important in the second one, but just to show that you are above threshold, and of course is critical for the third type of programs that we're seeing. I would say that bioenergy producers are generally supportive of the trend, but in some cases they do have some concerns about the quality of the LCA models and the ability of regulators to keep up with innovation. So what are the benefits of doing life cycle analysis? Originally it was to help decision makers select options that provided the lowest environmental impact. So LCA was used when we had just volume mandates. Companies can claim that one product is better than another on the basis of an LCA. From a company perspective, LCA processes help to narrow in on areas where the biggest reductions in environmental impacts can be made. And so they can be actually used to reduce production costs. So they have benefits other than just from a regulatory perspective. The limitations of an LCA, so LCA tools were not originally designed as compliance tools. Doing an LCA can be time and resource intensive, and the ability and the accuracy of the data that's available can influence the results. Most LCAs don't determine which product works best or is the most cost effective, and really LCAs are used as one component of the decision-making process, looking at the trade-offs between cost and performance. So moving on to data quality, of course, the LCA results are totally dependent on the quality of the data being used. And when we look at ISO LCA standards, they talk about primary and secondary data. So primary data is the information that is under the direct control of the person who is authorizing the study. And in our case, this is typically the biofuel producer. And secondary data is not information that is under the direct control, and in our case would typically be feedstock production related emissions, or perhaps fuel use emissions. So secondary data in LCA work is usually aggregated data from government studies or other studies or surveys that might have been done. Some of the challenges with all of this secondary data is that it can be old. So there's lots of data and models that are 10, 15, 20 years old. It can be taken from different regions that use different technologies. So it might not be applicable to what's happening in your particular area. In some cases, it is just an expert estimate. So somebody has made a guess at what's happening within that process, or it could be based on a very small data set. And if you start looking into LCA or lifecycle inventory databases, you can quickly find examples of all of these particular cases that call into question some of the LCA work. but quite a long time ago, 20 years ago, the community came up with a way to rank the data quantitatively. And so there's data is typically ranked in with 5 categories. So reliability, completeness, temporal, geographical, and technological. And it's rated on the basis of 1 to 5. So a really high quality data set will have 1, 1, 1, 1, 1, and a low quality data set is 5, 5, 5, 5, 5. And in fact, most data sets are somewhere in between the 1s and the 5s. So you get a mixture here. Regulatory LCA models. So most regulatory models that are being used today have at least a few issues with the quality of the secondary data. And in a few cases that I'm aware of, the impact can be quite large. So 10 grams per megajoule due to 1 data point within the data set. So when we're looking at biofuels that might have, carbon intensities of 20 or 30 grams per megajoule, if we have 1 data point that's out by 10 grams per megajoule, that's a huge issue for the carbon intensity of that particular case. So in one case that I'm aware of, the emissions are underestimated because of the quality of the data. And in another case, the emissions are overestimated. In both cases, the authority responsible for the models are aware of the issues, but have chosen not to correct them. And so this erodes confidence in the various programs that we have for targeting LCAs. So, we need to be working on addressing the quality of the data in all of these models. In the past couple of years, the IEA Bioenergy Task 39 had collected data from Renewable biofiles that were made available for public comment. And so these, in the Renewable bio process, there was third-party verification of the calculated carbon intensity. And as part of that process, they had to make their data and findings available to the public. And so during that public comment period, it was possible to download the data that went into the calculation of the carbon intensity of ethanol in Brazil. And so we collected data on 69 mills in Brazil, and there's a draft report that's been prepared, and we're going to be publishing that through Task 39. The data set has also been shared with a couple of model developers, and at least one of them is preparing to update their LCA model based on the information that was collected from the mills. So I believe that this is a very high quality data set. It will be transparent, and it will set a standard for others wanting to do the same kind of activity. But we need to have a continual effort to update these secondary data sets if we want credible life cycle analysis. There are lots of examples where the data is quite old in all of the models that were used for biofuel LCAs, and even in cases where we have new LCA tools that are being published and being used for policy development, some of the data is quite old. So last year, the European Commission had a new model that was developed for transportation fuels, and it had a lot of good aspects to it. But for the biofuels part of it, the data was almost all at least 20 years old and really not representative of what's happening today. Areas where LCA models need work, and so models can always be improved. You get started on this and it seems like it never ends. There is a global interest in increasing soil carbon with changes in agricultural management practices. The FAO has done some work in this area. The interest is at international, national, and net producer levels. Most regulatory models have a very limited capacity to model changes in soil carbon. And there are some people who believe that these changes in soil carbons can make a very large impact on the carbon intensity. And so it's not an easy task to model. Data quality is not great. Making actual measurements is very difficult because of the small changes that we get on an annual basis, but it is an important area where LCA models need a lot of work. There's also issues around electricity production. So, we have a lot of interest in net zero and zero emissions, and if really ignoring the fact that getting to zero is really hard to achieve. And some of the options that people think are zero emissions aren't really zero emissions. So hydroelectricity is often considered to be a zero emission source. But we have the issue of emissions from flooded lands. And in fact, just in 2019, when the IPCC released the refinement of guidelines for the calculation of national inventories, they added a new category. So previously, you had to account for land clearing emissions for the first 20 years, but we now know that there is new biomass added to reservoirs every year that results in methane emissions. And so now governments are supposed to be calculating emissions from flooded lands that remain flooded lands. And I would also say that the emissions from the maintenance and the operation of electric power systems are generally ignored. I have looked, and it's really hard to get some good data, but the limited amount of available information indicates that these emissions, so this is the maintenance of the transmission lines and just the operation of the systems to keep them working, are not as low as what people think they are, and is something that needs to be incorporated. And of course, both of these make getting to zero much more difficult. Bioenergy systems are complex. Regulatory programs that focus on the GHG emissions have been very effective at putting a price on carbon and creating incentives for producers to reduce their emissions. And this is exactly what we want to happen. However, it means that systems become more complex and challenging to model and more challenging for regulators to assess. And so if the models can't keep up with innovation, we're going to be challenged to achieve the reductions that we need. Regulators can't just put a model out there and expect it to be static and still give them good results 5 years from now or 10 years from now. So challenges moving forward, ensuring that the secondary data in the regulatory models is of high quality. And this is a constant challenge as the world continues to change. Ensuring that regulators can keep up with the rate of change in the production systems. And this is a classic challenge, and it's not just related to LCAs or to bioenergy systems. And ensure that the models, as a result of trying to simplify them and make them user-friendly, don't encourage higher GHG emissions. So I know of one case where they've simplified the models to the point where it gives a better score if you actually have higher emissions because of how they've developed some of the secondary data. And so that's the end. Over to you, Jim, see if there's any questions, and hopefully we've got 15 minutes left for the panel.
Yes, thank you very much, Don. There is one question here before we start the panel, and And after this question, we can see the results of the poll as we assemble the panel back together and go through further questions. So Helen Biwi Comesa, and again, apologize for the pronunciation, asks about regarding LCA not dealing with performance, can this partially be dealt with by selecting a precise functional unit that clearly specifies performance of the products and thus enables to compare two products with similar performance or something like that? So I mean, it seems to me an extra dimension of analysis that might not be LCA, but your thoughts on that, Don?
No, I mean, it is. And so this, in LCA programs, generally they're focused on the fuels and not necessarily how far the fuel might transport a vehicle. So, if we picked a more precise parameter like grams per kilometer traveled rather than grams per megajoule, then that helps to bring in performance. Generally speaking, regulatory programs that do deal with this use what they call an energy efficiency ratio to determine the performance of your system versus the reference system. That's one way of doing it. There are data issues, and I'm looking at some of those right now for one particular system. And one of the things that we found with electric vehicles is that over the last 10 years, we see fewer electric vehicles that are on the market that are converted gasoline vehicles, and more that have a unique platform just for that EV. So now how do we compare the performance of that against something that's not exactly the same, but it's close on the gasoline side? So yes, it can be done. More data is required, and some of it's not easy to get.
Yeah, that's a good familiar conclusion. More data required. More experiments, please. All right, well, thank you very much. I guess I want to switch over to the sort of the panel area. So if the previous presenters would also turn on their cameras, and we can go through the Q&A. There's been some I've noted, at least there's one comment that Glaucia has said she's going to respond live. I'm not seeing more along those lines, but it looks like a lot of the questions have been answered. And so if you haven't seen, go into that Q&A for that. So, and then we had, just to set this up, we had the poll. So maybe we'll go to the poll after, Glaucia, you answer this one question live that you were going to answer, please.
Okay, thank you for the question, for the opportunity to try to answer this very complex issue of the Amazon. Most of the Brazilian emissions comes from fires in the Amazon region. This we have a general consensus that this needs to stop. Agriculture here is not the culprit. It is logging and mining activities. We have the biofuel sector took this to heart, that we needed to contribute to stopping deforestation. The biofuels under the Renewable Bio scheme cannot be qualified for the rewards if they have been using land that was deforested after 2017. There is an oil palm zoning that has to be considered. All the lands have to be registered under CAR. There is an agroecological zoning for the energy crops. So, and there's a lot of pressure from the sector and the agricultural sector that developed quite a lot, modernized the agricultural practices to reduce emissions. We have in Brazil a program for low carbon agriculture that is also going very well. There is nowadays an Amazon a coalition of industries lots of new initiatives to develop sustainably, map, define what are the value chains in the Amazon that could be explored sustainably, and a large effort to develop the bioeconomy, including all the social, environmental problems of the region. So there is a lot of funds to be used for developing R&D and research efforts for the Amazon region. FAPESP is creating a program, an integrated program together with biodiversity, climate change, and e-scientists, computational scientists to answer to this challenge. And I think one immediate answer we have today, the promulgation of the legislation in Brazil that is working for the future, for the fuel of the future. And they just promulgated the biokerosene legislation to improve this sustainably. So I think I wanted just to frame that there is a lot going on in Brazil. We need to stop deforesting immediately. And this is not directly associated to biofuels at all. So we have a role to do and help research there, and try to improve the region sustainably, but not because biofuels will actually help, because they are using very low quality and have energy access insecurity in the region.
Thank you very much, Glaucia. Yeah, it's a very complex issue, and biofuels is a complex issue, and it gets tied into so many things. I'd like to ask our ETA Florence, okay, here we go. Here's the results of the poll. Hopefully everybody can see those. So quite a lot is expected from lignocellulosic biofuels in the future. Which technology would you expect to be the most successful in the coming decades? And we had a series of options there: gasification, Fischer-Tropsch, gasification and other synthesis, liquefaction, hydrolysis and fermentation, and other. And it's a roughly even split. There's a good liquefaction, it comes out the strongest, pyrolysis or HDL, and further processing of the biocrude at 34%. So Thijs, you'll be happy with that answer. I think it also is consistent with some of the marine shipping conclusions we've made, that it's a very attractive way to leverage current infrastructure. And other only got 7%. I guess I would have voted for I stayed out of this to not try to put my thumb on the scale, but I would probably say other, in the sense that we have a number of hybrid options and so forth. And I think this is very much an area of development, and we'll see more occurring. I guess, Dawn, just starting with the LCA, which is framing all of this, there are some developments that the European Union is looking at trying to, so this is on the topic of international harmonization, and around LCA, I'm aware that the GREET model that is used as the regulatory model in the United States, and it's maintained by Argonne National Laboratory, and it's our official model in the US, that the European Union is looking at making that more international. Can you comment on that, Dawn, on that effort? And that might lead to some progress on consistent rules, or at least appreciation how everybody's doing it.
So I think that IEA project is actually going to spend more time on the vehicles and some of the things like materials that go into vehicles and vehicle efficiency and some things like that, rather than on the fuel part of it. But for sure, you know, there's just a lot of data that has to be collected when you go into a new region. So the electricity system is different. The natural gas systems, you know, might be very complex. Oil refineries would have different product splits. So, you know, I know there's a lot of people who talk about a global LCA model, but we have enough problems trying to get accurate data to go into regional models, never mind extending that to a global model. And at the end of the day, you know, decisions are made by regulators. I know in Canada, we can't get two provincial regulators to come out with the same answer. Can't imagine what would happen when we try to do it internationally and get consensus on how to deal with some of these issues.
Well, it's a situation of perfect is the enemy of the good, and you know, we just need to be doing better. Perfection is going to be an ongoing struggle. So I guess,
and I struggle with that sometimes, you know, when we do in our third-party verification, you know, we have auditors that get all hung up about the second decimal point in terms of grams per megajoule, and they don't appreciate the uncertainty about some of the other numbers that they ignore. So, you know, we have a model where we know we're 8 or 9 grams wrong because the data was misinterpreted, and yet the third-party verifiers is spending thousands of dollars fussing over 1/10 of a gram or 100th of a gram. We need to get some balance in all this.
yes. So in the interest of we're running out of time, I want to give all the speakers an opportunity to comment on what they see as the, you know, any ahas moments out of the session, as well as what they see as the, you know, as the single biggest opportunity. I will just say that, you know, carbon pricing needs to happen. All this stuff is economically challenged, and to get it into the space of feasible economics, carbon price is a big deal. So I'll put that on the table, but I'd like to go through in the order that people presented. So Suni, your last sort of 1-minute thoughts on highlights from the session and your thoughts on what's needed.
You took me out completely there, Jim, because I was also thinking immediately about the carbon pricing. So I think I will just pass the word, and especially also in the marine sector, carbon pricing seems to be the obvious way forward. Whether it's going to happen, I'm not to say. I'm not so sure, unfortunately, but I'm really hoping.
Yeah, well, it's been a long time. So, well, thank you for that. Thijs. You might need to unmute.
Yes, thanks. Sorry. Yeah, well, summarizing, I think complexity is certainly an issue. Complexity, talking about regions, different types of biomass, different market needs, different ways of looking at LCAs, for example. I mean, I think the harmonization across the world, I agree with Don that that's going to be a challenge, although it would be very useful if we could achieve it. But I think in general, complexity makes life difficult, and maybe we should try everybody to somehow embrace it rather than trying to reduce it to get to something that is not workable anymore. I think that would be my take-home message.
Thank you. Glaucia.
Sorry, can you repeat the question? I was writing in the chat on it.
Sorry. Just your, you know, any highlights from the session that you wanted to emphasize, or your thoughts on what the biggest need is to move the sector forward.
Yeah, so one thing that I have been talking about in several venues is the need for data, the need to have access to data, generally good sources on data. We have so many indicators that could be evaluated and integrated to give more clarity to what is really sustainable. And all these criteria, I think, are laid out, but we need the data. So my general need right now is partnerships with the industry and with local governments to define good data sources.
Good point. Jose.
Yes, thank you. I'm not a technical engineer, but as I see it, we need quick solutions. So I think that the most quickest way is to produce drop-in fuels. That is a very quick way of reducing CO2 at the moment. And for further on in the long run, aligning, measuring the CO2 emissions, I think it's also one of the issues that is where it's done also working on, but I think that is also one of the issues.
Thank you. And finally, Don, last words.
Yeah, no, I mean, carbon pricing works, you know, in the markets that are doing that. There's lots of activity. It is complicated, and it does depend on, you know, getting the right yardstick in terms of what the carbon really is.
And that remains a challenge that we're addressing. So we're at time. So I'm going to conclude the session. I want to thank all the speakers again for really excellent presentations covering sort of a breadth of, you know, fuel opportunities in the shipping sector, for example, technology routes such as liquefaction through pyrolysis that can get us a lot of production in a hurry, especially if we can leverage refineries. The importance of you know, bringing in the whole global perspective of the opportunity of bringing in other countries other than sort of the major players today, such as LCA outlined, and the importance of certification to sort of validate sustainability claims and to allow regulators to have a measuring stick upon which to evaluate these different options. And LCA playing a critical role in all of that. So I think it is rather encompassing. In about 4 hours, we will have the next IEA Bioenergy Task 39 session. It will also be focused on transport biofuels with more of an emphasis towards aviation, which is one of the other sectors that we're really targeting for future biofuels development and deployment. So again, thank you all. And I just posted in the chat, I think, but there's, and I don't know this system, but there's a Wonder Me site that we can continue the discussion a little bit and networking. And I just posted that to the Q&A, and I will be heading to that shortly. So thank you all again for excellent presentations. It's been a pleasure moderating, and look forward to seeing you later in the sessions later on in this conference. So with that, I will close the session. Thank you.
Thanks, Jim.